Alright, we're going to look at electron configurations in this video. Now if we had to draw out an orbital diagram with boxes and the 1s, 2s, 2p under every, underneath the boxes every single time and drew in the arrows, it would be very time consuming as well as take up a lot of space. So we have a shortcut way of writing out the where the electrons go, how they're arranged. It's called an electron configuration. So this is a shorthand way of drawing these out. We actually have an even bigger shortcut that we'll learn after we've practiced this for a little bit. Our shorthand notation is going to consist of a few things. It's going to consist of numbers, letters, and a superscript, and a superscript is written above the letter. Now the number will tell us what energy level that we're in, so we only have 7 energy levels, so a 1 through a 7. The letter that we'll use is going to represent the sublevels, so you'll see S, P, D, and F. And then the superscript is going to tell us how many electrons are there. So for instance, if the p orbital had maybe 4 electrons in it, you'd see a p with a 4 superscript for that. This is what our fluorine example looked like when we did fluorine in our orbital diagram video. We had our arrows going opposite directions. We had a total of the 9 electrons, and so our 2p orbital wasn't completely filled. In shorthand, what we're going to do is we don't have to draw any boxes. We are going to keep what energy level we're in. We're going to keep what orbital we're in, and then the 2 here represents the number of arrows that we had to put in that box. So the 1s had 2 arrows, the 2s also had 2 arrows, and then the p orbital had 1, 2, 3, 4, 5 total arrows. So that's what our shorthand version is going to look like. And this picture again just kind of tells you what that what those numbers and letters represent. So the coefficient, the number that's out in front, that tells you what energy level you're in. The S, the P, D, or F, that tells you what sublevel you're in. And then the 2 up to 14, the F orbital, since it has 7 boxes, could have a total of 14 electrons, tells you the total number of electrons that you have present. So we're going to do some practice problems, only now this time we don't need to draw in all these boxes and everything like we had to before. We do need to know though that carbon has a total of 6 electrons, and so again you're going to want your orbital diagram really handy. Open it up to that note, to that part of your notes. Maybe you'll have to kind of flip between these pages. For carbon, again, you want to start with your lowest energy level, which is always going to be 1s, and the s orbital can hold a maximum of 2 electrons. From there, our next highest energy is 2s, and 2s can also hold a total of 2 electrons. So we're at 1, 2, 3, 4 electrons out of our 6. And so our electron dot diagram says that we have to go to the 2p orbital next. And because we only need 6 total electrons, we're going to have a 2 as our superscript. So we have 2, 4, 6 electrons there. For carbon, if we do chlorine, it had considerable more. It had 17. So I'll draw that in here so we don't forget. We always want to make sure that we kind of stop and count our electrons along the way, make sure we don't go over or under. Following our electron diagram, we have 1s2, and then we go to the 2s orbital, and it needs 2. 2p comes next, and it's going to hold a total of 6. So now we're at 10 of our 17. We have 6, 7, 8, 9, 10. So that means if we're looking at our electron diagonal rule, the diagonal rule, 3s comes next. So 3s, and it can hold a total of 2 electrons, and that puts us at 5 more in order to get our 17. So 3p, and that can hold just 5. It can really hold 6, but we don't need that many. We only need 17 electrons, so 5 is enough. Magnesium, if you look at your periodic table, has 12 electrons, and so if we're drawing our electron configuration, we're always going to be doing the 1s, where we're starting there always. That's the lowest energy. Then it can hold 2, 2s can hold 2, the 3p can hold 6, sorry, that's a 2, and we're up to 10. So now we move up to the 3s orbital, and it can hold 2, and we need all 2 of those. We need a total of 12. So there's 1, 2, 3, 4. Another 6 makes 10, 11, 12. So we have a total of 12 electrons with magnesium. Alright, let's move on to argon. Argon is a noble gas. It is 18 electrons. And so for this one, you would have 1s2. We have move up to the 2s2, 2p6, and we're at 10. We have 8 left to go. So now we're at 3s. All of those can get filled up, the 2, and then the 3p would have 6, which we do need all of this time to get our 18 total electrons. So again, if you're following the diagonal rule, it's going to tell you which orbital comes next, which energy level and orbital. All you're responsible for doing is putting in the the superscript. S's can hold 2, P's can hold a maximum of 6, D orbitals can hold 10, F orbitals can hold a maximum of 14. So let's go to nickel. Nickel's going to bring us up into using one of our larger orbitals, and then we'll call it done here. So we have 28 electrons in nickel. So we know argon has 18. So we know we can definitely use everything that we had for argon. 1s2, 2s2, 2p6, and if we occasionally there check it on our diagonal rule, we know that when we get to 3p, the next orbital energy and orbital that we're going to get to is actually the 4s. Notice that sp, the d orbital, comes next in the row, but if we're following the diagonal rule, we're going to hit the 4s energy-wise first. This is the Aufbau principle, where we need to make sure that we are going from lowest energy to higher energy. And we're going to use all 2 of those that the s orbital can hold, and now we get to the 3d. And if we total up how many we have here, we had 18 when we got to the end where argon was, so these 2 would give us 20. That means we have 8 left. And the d orbital can hold a maximum of 10, because there are 5 different shapes. Each one can hold then 2 electrons, but we only need 8, so we are going to have it's not a completely full, but 3d8 is where we would end. And that's what an electron configuration looks like, so it does save us quite a bit of time. You don't have to draw any boxes and arrows in.